Hi everyone, this is Pranavi. Today's our topic is variation of carrier concentration with temperature in an intrinsic semiconductor. Variation of carrier concentration with temperature in an intrinsic semiconductor. Carrier concentration. The density of a carriers in the semiconductors as a function of temperature and material properties is Ni square equal to bt cube exponent of minus Eg by kt centimeter minus 6. Eg is equal to semiconductor band gap energy in ev, that's electron volts. K is equal to Boltzmann constant. T is equal to temperature. B is equal to material dependent parameter. Increasing the temperature makes it more likely that an electron will be excited into the conduction band, which will increase the intrinsic carrier concentration. Carrier concentration when its temperature is increased to a value at which the intrinsic carrier concentration doubles. The intrinsic carrier concentration formula is Ni equal to square root of Nc into Nr into e power minus Eg by kt. So when we add the rest all, that is ionization, intrinsic and extrinsic semiconductors, we get this formula. Ni into T is equal to E2 into 2 pi kt by h square whole power 3 by 2 into mn mp whole power 3 by 4 into exponent of e power minus eg by 2 kt. Ni depends on temperature and Fermi level depends on temperature. So if we dope any semiconductor with any impurity atom, then the initial electrons are loosely bound to nucleus, and only upon raising the temperature electrons come out and move freely. As this temperature also becomes ionized, Ni depends on temperature and Fermi level depends on temperature. So if we dope any semiconductor with any impurity atom, then the initial electrons are loosely bound to nucleus, and only upon raising the temperature electrons come out and move freely. As this temperature also becomes ionized, so Ni is strong depends on temperature. The temperature at which the atom becomes ionized, then it is called temperature of ionization. Now we can see variation of carrier concentration of temperature by a curve drawing a carrier concentration and a T inverse. Here we can see that on x-axis we have temperature and on y-axis we have carrier concentration, that is N0 is taken, and Eg is taken to explain the variation of concentration. Silicon is doped with N-type. Donor concentration at 0 Kelvin temperature semiconductor behaves as insulator, and an N naught is, that is carrier concentration, depends on two factors, that is thermal generation and donors. Here you can see that as well temperature increases. If the temperature increase means the temperature is in denominator. We can see that rightmost point low and the left is high. So when we move from right to left in this curve, we have three reasons. This topic can be explained by these three reasons, that is ionization, extrinsic and intrinsic. We can see in first reason, that is this rightmost point, that is we can see that is first reason. That is because the donor atom concentration is high in compared to thermal generation carriers, that is D is greater than Tg. when the increase in temperature more than 100 Kelvin or equal to 100 Kelvin, at that point it is ionized. So here it is low. Then when we come to the second reason, that is the middlemost point, here we can see that N naught is equal to NT, that is it has a constant temperature all over. The reason on creating by a dupe as well as the temperature is high more at room temperature is 300 Kelvin. At this particular value it gives 3.3 approximately. If the temperature is increased more, then it becomes to third region, that is at the leftmost point top. Concentration of thermal generation carriers will become more in comparison to donor atoms. So finally at leftmost point it is higher temperature, that is Ni is higher than the NT is donor concentration. The intrinsic semiconductors dominates the rest to concentration.